Hello, in this video I want to look at the different trig ratios and what are possibilities for the values of the trig ratios. So let's take a look at what we mean by that. Well, let's say you look at, for example, sine of an angle, okay? Remember, that's defined as, you can either look at it as opposite over hypotenuse, or more likely you'll look at it as y over r when you have a right triangle on a circle. So if you look at, then let's take a look at the circle and just get our bearings here. Remember that when the unit circle is 1, when the radius is 1, you have the unit circle. And so what you're really looking at are just the y values as you start rotating. So what happens then is, as I start rotating, I start here at 0, let's say radians, and the y value is 0. And in fact, you know that the coordinates here at this point are 1, 0. So you have all x and no y. But as you start rotating, right, I start rotating like this, and you look at each point here. So if I look at this point, this is the y coordinate. If I look at this point, this is the rotation up to that point. And what you're seeing is that the y coordinate is doing what? It's increasing, right? It's getting longer as you're going from here, 0 to pi over 2 or 0 to 90 degrees. And so what's happening is you start out with, a right triangle that's basically has no y, right? And it kind of doesn't really exist, but, theoretically. And then it starts to get a little bit, gain a little bit more length in the opposite or the y, a little bit more, and then a little bit more, and then a little bit more, and finally until it's, a lot of y, until finally it's all y, right? So when you look at the ratio, though, of y over r, and r is constant, the radius, or the length of the radius isn't going to change, right? The radius of the circle, that's always going to be 1. So really you're looking at a length y over r, and y is always going to be smaller than r, because if you remember, for any right triangle, right, the longest side of the right triangle is going to be formed by the largest angle, which in any right triangle is going to be the 90-degree angle where the vertical and the horizontal line come together. No, that doesn't look horizontal, sorry. And then these two remaining, like theta here and beta, they have to add up to 90 degrees because a triangle has 180 degrees total. So what that means then is that when you look at the ratio of y to r is always greater than y, except for here at like 90 degrees or pi over 2, in which case finally you get to where they're both the same. So r is always greater than or equal to y, right? So therefore, if I now divide both sides by r, I get that the ratio y over r is always going to be less than or equal to 1. So sine of an angle can never exceed 1. And the same is going to be true for the negative values, right? Because the only difference there is you're going around the circle, right? And now you start diminishing, the y value starts diminishing, but it's still positive, and then it starts becoming negative, and the greatest it'll ever be is -1. But remember, r is always positive, and it's always constant, so it's always +1 on the unit circle. So you're really comparing what's the length of the y coordinate relative to the radius. And really, for any right triangle, here's your r, here's your y, here's your x relative to, let's say, theta. And so let me go ahead and get beta out of there so it doesn't seem confusing. This length is always smaller than what? This length. It's got to be true. So therefore, the ratio of y to r is always between, so what you'd have is y over r is always going to be between -1, and 1. That's all that's possible, okay? All right, just checking to see if the video is really recording well. So obviously cosine is going to be the same, and I'll let you go through that thought process. I'll just kind of start you out that when you have cosine of an angle, that's defined as x over r. And on a unit circle, for example, here you have cosine is the x. Now the r is always the same, right? It's the distance from the center of the circle to the edge, right? But the x changes. At first, when you start out at 0 radians or 0 degrees, you have the movement is all x and 0 y. Again, that's why the point is 1, 0, right? But then what happens? It keeps getting what? Smaller, right? Until it gets down to 0. And so finally, here, you'll have 0 over 1, which is just 0. So again, you'll find that cosine essentially is going to end up the same as sine, where x over r is between -1 and 1, right? Okay. Now, let's take a look at secant and cosecant. So let's look at cosecant of an angle. Well, that's described as r over y, which, as we know, is the reciprocal of sine, right? So here, what you're always doing is, for any, no matter what right triangle you have, so let's even exaggerate it a little bit more in the y. So here's your right angle, here's r, let's say you're looking at theta here, here's y, and here's x, assuming you're on a circle. Now what happens here is that r is always what? Across from the right angle, so it's the longest side, and so r is always greater than y. Right? So obviously you're going to have all numbers that are bigger than 1, since the numerator is always bigger than the denominator. What can happen, though, is as you're rotating, right, and since we're talking about y, as I'm rotating, I start at 0 and I go all the way up here to, let's say, pi over 2, or 90 degrees. The coordinates are 0, 1. At that location, the r and the y are the same length. So at that one location, you have 1 over 1. So their cosecant bottoms out at 1, because for every other rotation, as you start rotating away here, the length of the y is starting to what? Get smaller, right? And as it was increasing, as it was starting at 0 and coming toward pi over 2, it started out at 0 and started increasing. But at all times, for all locations and all rotations, the length of the y was always what? Less than r. It only became equal to r at pi over 2. So you have that issue. Now what you can have happen is that what? Starting here, remember, this is the coordinate 1, 0 at 0 radians. Here you'd have r, which is this length right here, let's say 1. So when you look at cosecant of, let's say, 0, you have r over y, but r is 1, but here y is what? 0. Now what do you have there? You have an infinity, right? So this is undefined, and of course we say undefined because we literally can't bound it. We can't define it. If we try to say, oh, this is the value, it's like, no, 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 it can get bigger because it goes to infinity. Or, you know, so that's why it's undefined there. And of course you can do the same thing with secant, and then I really will let you do. And I do want to take a look at tangent, and then I'll let you consider cotangent. So tangent of an angle is defined as y over x. Now here, this is a little more interesting, I think, because you don't have, your definition here doesn't have r in it, right? Which r is always constant. R is always the radius, it doesn't change. But here, both x and y change. So here what's happening, let's see if I can make a bigger circle. So let's take a look at, you start at 0 and you start rotating, right? What happens here is you're all what? All x and no y. So right here, you're dividing by 0, right? And when you have 1 divided by 0, you already start out at an infinity, right? But then as you keep, rotating, I'm here. So in this triangle, you have a little bit of y, and now Oh, I'm sorry, I said that wrong. Y over x would be 0 over 1. I'm sorry, you started at 0. My apologies. Here at 0, tangent of 0 is 0 over 1, which is 0. So here you start out tangent is 0. Sorry, it gets to infinity over here. And as you start rotating, what happens is you start increasing the y, but that also, so you're increasing y, but you're decreasing x. So this ratio is starting to get bigger in the numerator and smaller in the denominator. And here you get a little bit more y, a little less x, until you get to pi over 4, or 45 degrees, right? At that location, let's get a different color, the x and the y lengths are the same. So over here, where you do tangent of pi over 4, you get, well, square root 2 over 2 and square root 2 over 2. And you get 1. But visually, you see it in the triangle, the lengths of the triangle, because these lengths are the same, right? So the y over the x. And now, once you get past this here, let me go to a different color. Once you get past pi over 4, what happens now is the y, right, is now longer than the what? X. Y is longer than x. Y is longer than x. Until it's all y and no x, right? So here, then, for these values, so from here to here, y is greater than x. Here, y equals x. And here, y is less than x, right? So then what kind of ratios do you get? Well, you get fractions. Here you get 1. And here you get numbers bigger than 1 until they get so big, the numbers get so big, they go to infinity, because right here at tangent pi over 2, where your coordinates are 0, 1, you get y over x, which is 1 over 0, and that's undefined or infinity, right? So it's interesting here, and of course, as you keep rotating, what'll happen is that you'll have to account for the signs, positive and negative. So of course, you have the same ratios, you know, where here y is bigger than x, but the x is negative. So you get very large numbers greater than 1, but they're negative. And then you get -1, and then you get here from here to here, where the x length is bigger or longer than the y length. You have fractions, right? Numbers less than 1, but they're negative because x is negative. And of course, if you come over here, both x and y are positive, so you have the same kind of ratios going on, but everything's positive. And then here again in quadrant 4, you have negative, because then the y is negative, but the x is positive. But the same idea in terms of the comparison of the lengths of the y to the x, okay? So that's the possible values for the different, of course, cotangent is the same, it's just that you have to look at the reciprocal x to y instead of y to x, but it's the same idea, right? You're comparing the lengths in the right triangle. So one thing I just want to touch on and end on is that you may wonder, well, gosh, we keep talking about the unit circle. Is this true for all circles? It really is, because I just want to remind you that if you were to look at a bunch of concentric circles, right, do my best to, okay, and we were to put in the x and y axis, when I look at a particular angle rotation, like that, right, when I go to use the rule and drop the perpendicular to the x-axis, what I'm creating are what? I'm creating similar triangles, right? And even though the lengths of each of the right triangles is different, as well as the radius of the circle, so the size of the circles are different, they're different, right? So here, obviously, this is a small, short length versus here, this is a long length. But the ratios, the corresponding ratios, remain the same because the triangles are similar. So this, and for any size circle, what'll happen is, so let's just pick one. Let's say I'm here. Again, you could look at the relationship, for example, with tangent y over x, this y to this x. Still going to hold, right? If it's at 45 degrees, they're the same. If it's less than 45 degrees, you have what? You have not so much y and a lot of x kind of thing. Or if you get past 45 degrees, you have what? A lot of y, very little x, that kind of thing. And that's true for all the different ratios. So just think about that, because it's really more about, I think if you can visualize the lengths of the sides of the right triangles and just see how the lengths compare to each other, you really can see what is possible. All right. Thanks so much for listening.